Hello and welcome to this lecture on chemical process modeling and simulation. This is the second of the lecture series on conservation equations. In the last lecture, we derived the continuity equation or the conservation equation for overall mass. That was given as a prelude for the subsequent analysis of a derivation of a general conservation equation in fluid transport systems. Now, in this lecture and the subsequent lectures, we will start putting in place the pieces that are needed for us to derive the general conservation equation. And one of the important pieces in play that we need in place is the idea of substantial derivative or Lagrangian time derivative. We are going to see this in this particular lecture. There are two perspectives with which we can analyze, visualize flow of a fluid. One is an Eulerian approach, the other is the Lagrangian approach. Eulerian approach is a position-based approach. What do I mean by this? Fluid is studied at a fixed point xyz or r theta z or r theta phi depending on the coordinate system, fixed point at all times. Therefore, since our attention is focused on this fixed point, we study whichever particle is present at that point at any given time. So a particle may come, reach that point at a certain time, and then it may depart, and another particle may come and it may depart, and so on and so forth. This Eulerian approach is something that you are familiar with. You have seen this in, for example, thermodynamics, or also in all your other courses in fluid mechanics, heat transfer, mass transfer, reaction engineering, transport phenomena, as a control volume analysis. So you take an infinitesimally small control volume and then you look at what is coming in, what is going out, and then you write your balance equations accordingly, right? And this approach is the Eulerian approach. So extending this idea further, we could study the rate at which a fluid particle crosses x, y, z at any given time t. This would be the instantaneous velocity of that fluid particle v of t at that point x, y, z. So in other words, we watch the fluid flow from a fixed point. The other approach is the Lagrangian approach. Lagrangian approach is a particle-based approach. Rather than fix the position and look at what particle comes and goes, we fix the particle. And then we move along with that particle, however that particle goes. So suppose a fluid particle A is identified by its initial position at time t equal to 0. Now notice, I have first given an identity for the particle. I have called it A. And that particle, how do I assign this A? I am looking at some arbitrary time t equal to 0. And I am looking at what its initial position vector is. And that initial position vector I am taking to be R0, R being the position vector. Now you can of course express this in any particular coordinate system, but wherever I am giving these kind of examples, I have always stuck to Cartesian coordinate system for us to easily visualize and understand this, right? So even in continuity equation, I did the same, and subsequent lectures also it will be the same. So, but by no means is this all these arguments restricted or limited to only Cartesian coordinate system. Okay, please keep that in mind. So the r vector or the position vector is given by the points, the coordinates, x, y, z at a given time t. So r is r of x, y, z, t. At time t equal to 0, I call these x, y, z positions as x0, y0 and z0, and that is simply therefore r0 is equal to x0 I plus y0 j plus z0 k. That is the initial position vector. That is where the fluid particle is when I start observing that particle, and then I move along with that particle. As the particle moves at a future time, its position vector will be obviously different from r0, and that depends on how x evolves from x0 to a new position which is given by x of t, how y evolves from y0, the initial position in the y coordinates, y-axis, along the y-axis rather, to a new y of t, and z evolves from z0 to z of t. So this evolution is what we are interested in tracking because we are going along with the particle. So here is a pictorial representation. There is the particle A. There is the particle A at time t naught, and then this particle moves along some trajectory and reaches this new position at time t. So the coordinate system, if the origin were somewhere for here, for example, then I can take this vector, position vector r0 to be given by x0 I plus y0 j plus z0 k, and the new position vector r vector would be xi plus yj plus zk. So now we drift along the fluid at its velocity. Now this is also something that is not very unfamiliar to all of you from your school days. Here what we are looking at is, we are looking at as if we are sitting on the particle and then we are moving along with the particle. Therefore, since we are drifting along the fluid at its velocity or the fluid's velocity, this basically is sort of talking about a relative velocity coordinate system, right? Where, for example, you are sitting in a train which is moving, and then you see an opposite train come by, and it seems as if you are stationary and that train is moving at much faster velocity than it actually is moving, because now we are looking at a relative velocity field, right? So you are sitting on your particle, so to speak, which is the train in this particular example, and then there is the other train that is moving, which is, so you observe what is happening all around you as you move alongside the particle. So this is the Lagrangian approach. Both these approaches are actually quite familiar to you. Now what we are going to do in this lecture, for the remaining part of this lecture, is to relate the time derivative that you estimate from the Eulerian perspective to the time derivative that you estimate from the Lagrangian perspective. Let us denote any fluid property, whether it is momentum or temperature or heat flux or concentration or any property, as q, which is q of x comma y comma z comma t. And notice that I have not indicated whether this property is a scalar quantity or a vector quantity. I've given examples of both scalars and vectors in this. It doesn't matter. From a Lagrangian standpoint, let us track the particle A, whose fluid property is momentum or temperature or whatever concentration is denoted as q. From time t equal to 0, consider where the particle A would be at an infinitesimally future time delta t. So in just a very short time, future time delta t, where will this particle go? Let it be, the original point be O, okay, x0 comma y0 comma z0. Let us call this O, which is at t equal to 0, which is the origin, and the new point, let it be called as O dash, which is x comma y comma z at t equal to just that infinitesimally future time delta t. Once again, I want to point out, just because I am using Cartesian coordinate system in establishing this relationship, does not in any way limit the generality of this, the validity of this relationship. So if at time t equal to 0, position vector of the particle A is r naught, x naught I plus y naught j plus z naught k. Now the velocity vector is vxi plus vyj plus vzk. Then the new position vector. Remember I talked about how the x position evolves from x naught to new x. So what is that new x? Starting from this point over a very small time delta t, if the velocity is vx, then basically the displacement, x displacement is vx into delta t. Similarly, the y displacement is vy into delta t, and the z displacement is simply vz into delta t. So therefore, the new position vector now would be x naught plus vx delta ti plus y naught plus vy delta tj plus z naught plus vz delta tk. Now, if you have to calculate the time derivative, you look at change in position with respect to change in time. And this Lagrangian time derivative is denoted by the capital D by dt operator. Of course, this is limit delta t tending to 0 for this infinitesimal time interval tending to 0. Now q at O dash, which is the new position vector, which is this new point, right, minus q at the old point divided by delta t. So this is your Lagrangian time derivative. Note that q is equal to q of x, comma y, comma z, comma t. Now if I were to expand q as the Taylor series around t equal to 0, because that's where I start, and then I set delta t tends to 0. So if I were to write this Taylor series expansion and then neglect the higher order terms, then basically I am left with my initial value. This is x q at x naught, y naught, z naught, t equal to 0, plus dou q dou t multiplied by delta t, dou q dou x delta x, dou q dou y delta y, dou q dou z delta z. This is basically dq. This is how much change in q has happened. Neglecting the higher order terms, second and higher order terms, and substituting this back into this particular time derivative definition, what will we get? We will basically get all these terms will be gone, and then this of course is subtracted here, so that will be gone. So I will have, let us take the first term. I have dou q dou t multiplied by delta t divided by delta t, so that will go off, and then I have dou q dou x multiplied by delta x by delta t, which I have there, and similarly dou q dou y delta y by delta t, dou q dou z delta z by delta t. Now limit delta t tending to 0, if I apply this limit to these terms in the square brackets, I will get limit delta t tending to 0, the x displacement with respect to time, that is my vx, y displacement with respect to time, that is my vy, z displacement with respect to time, that is my vz. And therefore dq dt is dou q dou t plus vx dou q dou x plus vy dou q dou y plus vz dou q dou z. And as you can see, this is a dot product or inner product of v vector, the velocity vector, and the vector which is basically the gradient of q, dou x of qi plus dou y of qj plus dou z of qk. So this is simply v dot del q. So this basically gives us the relationship between the Lagrangian time derivative denoted by the capital dq dt and the Eulerian time derivative, which is conventionally denoted as del q del t. Of course, this is evaluated at a fixed x, y, z. Remember, and that is the Eulerian perspective. I am evaluating this partial derivative at a point. That is my Eulerian perspective. And this is basically the Lagrangian time derivative is evaluated for a particle, irrespective of where that particle is, which point that particle is in. So the relationship between these two is captured additionally by this term v dot del q. So the left hand side is this time derivative is estimated for particle A, that is your Lagrangian time derivative, and the right hand side partial derivative is estimated at fixed point xyz, and that is your Eulerian time derivative. Therefore, if I were to look at the Lagrangian differential operator d by dt and Eulerian operator dou by dou t, they are related by this particular relationship. D by dt is dou by dou t plus v dot del. Of course, d by dt operating on some function, whatever be that quantity, whether it is a scalar valued quantity or a vector valued quantity, does not matter. And this is basically defined by your Eulerian partial derivative plus the dot product or inner product of the velocity field and the gradient operator, gradient of operating on whatever that quantity that you are looking at, whose Eulerian and Lagrangian time derivatives are being related. So this gives us the Lagrangian time derivative, that gives us the Eulerian time derivative. That brings us to the end of this lecture. As always, I'd be very happy to answer any questions you may have. If you have any questions, please feel free to leave them in the comments page, or you may write to me, contact me. I'll be very happy to clarify any doubts you may have. Thank you for listening to this lecture, and you have a wonderful, wonderful day. Thank you.